All right, so the plan for today, wrapping up the last little bit of chapter 11 these next couple of days. So we'll finish 11.8 power series and talk about 11.9 representing functions as power series. When we come back on Wednesday, we'll plan to discuss Taylor and Maclaurin series, possibly with a supplement on that material. And also we'll do a quick, I'll post a quick series review that'll have some, just different series listed, and then you can work back through and look through kind of all the different tools and techniques and see what applies to which series, proving convergence and divergence, possibly being able to get a sum if, if all of the stars align, if it converges and it's the right kind of series, you might be able to get a sum out of it as well. And then the last couple of class meeting days, we will jump into chapter 12. So this is material that would, kind of fits a little bit better with Calc 3, but I think I've mentioned before that once we added vector calc at the end of Calc 3, that pushed a little bit of material into Calc 2 and even a little bit of Calc 2 material into Calc 1. So we'll hit some of this chapter 12 material at the end of Calc 2, and that'll be our last bit of material for the course. But really the kind of wrap up to the major themes for Calc 2 is this and these last couple of sections at the end of chapter 11, particularly on Taylor and Maclaurin series. Very important in a lot of different applications in things like physics, engineering, a lot of the hard sciences use these Taylor series and their approximations quite a bit. And then, of course, we have the final exam coming up. It's a pretty quick turnaround before we're at the final exam already. The final exam will be available from Friday the 2nd through Friday the 9th. This starts a couple of days before the proper final exam week, but this way you'll have the weekend, Friday, Saturday, Sunday to complete it if that works better for you. Similar setup to the midterm exam, taken on WebAssign. Oh, not using Examity. Let me fix that. Taken on WebAssign. Post the sample exam the week before. You can use a formula sheet, and I'll post more details about that as we get closer to the exam. So that's a quick rundown of what the rest of the semester is going to look like. The quote of the day today is "Luck is when preparation meets opportunity." It's attributed to the Roman Stoic philosopher Seneca, Lucius Annaeus Seneca. But as far as I can tell, there's not really a good argument behind attributing it to him. So who knows where it came from? But I think that it's an interesting thought nonetheless. You look at people in certain positions, and when you look at their life story, you say, oh, well, you were very lucky that you ended up in this position, but that was only because these 5 things all kind of happened, and you were very fortunate or lucky to have that happen. But I think looking backwards, we can often forget that when opportunity comes around, you have to be prepared to meet that opportunity, right? Opportunities, similar opportunities may come around to other people, and if they don't have the right preparation at the right time, that opportunity just passes by. So focusing on being prepared to meet opportunity when it comes around, when it arises, I think that's what often feels like luck. So now, of course, it can certainly be true that if more opportunities come around to one person than another, the chance that their preparation will meet the opportunity is higher. But what we can control is our preparation. So making sure that we're ready whenever opportunity comes around, and we're ready to move on that. Okay, so let's zoom in here just a little bit. There we go. Let's do a quick recap of power series, what we have discussed up to this point. I don't want to spend too much time here, but since it has been a week and a half, just a quick recap to remind ourselves how all of this works. So remember, a power series is a series of the form some Cn x to the n, so C naught plus C1x plus C2x squared, or possibly some Cn x minus a to the n, where we would say the power series is centered at A. So this up here would actually be a special case where the power series is centered at 0. Again, recall that the sum is a function. It's a function f of x whose domain is the set of all x for which the series converges. And we had an interesting theorem here, which roughly says that power series converge on symmetric intervals about their center. So we have this idea of a radius of convergence for the series. So the series will converge for x within our units from the center. It'll diverge for x's that are more than our units from the center. And at the endpoints, it may or may not converge. And we have our kind of two special cases, radius of convergence of 0, where the power series converges at and only at its center, or radius of convergence of infinity, where the power series converges for the whole real line. Okay, so let's continue from where we left off last class, a week and a half or so ago. So hopefully you didn't take a full week and a half completely away from the material, and this is, not too rusty in your mind. So here we have a power series. We note that it's centered at -3. We've got to be a little bit careful here. Right, some Cn x minus a to the n, so x plus 3 to the n means a is -3. And we like to find the radius of convergence and the interval of convergence. Remember, the way that we usually go about this is we start with finding the radius of convergence, and for that, we typically use the ratio test, because that takes the ratio of the next term to the current term, which means that a lot of this x to the n business just kind of divides out and gives me something pretty easy to work with. So we'll call each of these a sub n. So if I look at the absolute value of the ratio of an plus 1 to an, that gives me -2 to the n plus 1 over root n plus 1, x plus 3 to the n plus 1. So that's an plus 1 up top. And then 1 over an gives me what? Well, it gives me an x plus 3 to the n on the bottom. It gives me a -2 to the n on the bottom. And it gives me a root n on top. All right, so what all do I have here? Well, the -2 to the n plus 1 over -2 to the n comes out of the absolute value just as a factor of 2. Then I get root n over root n plus 1. And then I'm left with absolute value x plus 3. So that's what all of this simplifies to. And for my ratio test, I want to ask what happens to this as n goes to infinity. Well, this root n over root n plus 1, this goes to 1 as n goes to infinity. The 2 and the absolute x plus 3 don't have any n's left, so I just get 2 absolute x plus 3. And remember, the conclusion of my ratio test is that if this ratio is less than 1, we converge absolutely. If it's bigger than 1, we diverge. And if it's equal to 1, we're not sure. We have to do something else to figure out convergence or divergence there. Or in other words, if absolute x plus 3 is less than 1/2, we converge absolutely. And if it's bigger than 1/2, we diverge. So this is our radius of convergence. Our radius of convergence is 1/2. Our center is -3. So what can I say? I can say that I converge absolutely on -3 minus a half, -3.5, to -3 plus a half is -2.5. On that open interval, I definitely converge and converge absolutely. I diverge on kind of the open complement when I'm more than a radius of divergence away, minus infinity to -3.5 open, union -2.5 open to plus infinity. I diverge there. And as is often the case, I have these endpoints that I need to check. So I need to check what happens at x equals -3.5 and at x equals -2.5. So I'll check those two to see what happens there. So let me come up here and let me see if I can copy this down. And I just pop this over here to make it easier to reference. Wasn't having too much good tech luck in my stats class, but cross my fingers, that seems to be working now. All right, so let's evaluate these two bits individually. For x equals -3.5, I have some -2 to the n over root n. And then I have -3.5 plus 3 is -1/2 to the n. I can combine the -2 to the n and the -1/2 to the n. So these two bits will combine to give me, well, that's just 1 to the n, right? -2 to the n times -1/2 to the n is 1 to the n, or that's just 1 over root n. But wait, this is a p series where p is less than 1. Well, I suppose less than or equal to 1, we could say. This diverges. So we diverge at -3.5. What about a -2.5? Okay, so again, we have some -2 to the n over root n times -2.5 plus 3 is +1/2 to the n. -2 to the n times 1/2 to the n, or -2 to the n over 2 to the n. Well, that gives me a -1 to the n over root n. And we can see clearly this is an alternating series. This converges by the alternating series test. And so I'm going to use the eraser method here. We converge on open -3.5 to close -2.5. I suppose we can't say we converge absolutely on that interval, but we do converge on that interval, and we diverge at -3.5, so we can close off that bracket there. So we use the ratio test to do, in some sense, most of the heavy lifting, but that, often can feel like the shorter part of the problem. The longer part of the problem, the greater effort on our part is to handle these just a couple of points here, as that's often the case. Okay. I don't know why I have this copied again down here, but so one last problem in this section. So this is a little bit more of an abstract problem. Suppose that we have a series, sum n equals 0 to infinity, cn x to the n. for some specific set of CNs. And suppose that we know that this series converges for x equals -4 and diverges for x equals -6. What can we say? Well, I jinxed it by saying that the tech issues were over. So I don't know why this is starting at B, but it is, so that's fine. We can start at B. What can we say about each of these series? So maybe take just about 2 minutes or so and try to think through it on your own. This is a little bit more abstract. It's a little less just, kind of plow through the calculations. Maybe take about 2 minutes, think through it on your own, and then we'll discuss the answer. Okay, it's right around 2 minutes. So I tried to kind of write in a couple hints as we were going along here in case you got stuck with where to get started. But let's take a look at each of these. So the key to this problem is to realize that, well, number one, the center is at 0. We see that just looking at the power series x to the n, x minus 0 to the n. It converges for x equals -4. So I know that power series converge on intervals that are symmetric about the center. So that tells me that my radius of convergence has to be at least 4. It can't converge at -4, have a center at 0, and like diverge at -2. That's not how it works. That's not what our theorem says. On the other hand, I know that it diverges for x equals -6. My radius of convergence must be less than or equal to 6 then. Okay, so let's look at, I suppose, part B here. Sum n equals 0 to infinity, Cn times 8 to the power n. Does this converge or diverge? Well, if this converged, I see that 8 is 8 units away from the center of 0. If it converged, I would need a radius of convergence of at least 8, but I know that the radius of convergence has to be at most 6. This must diverge. My radius of convergence is at most 6. We would need a radius of convergence of at least 8 in order for this to converge. So no, it can't converge. What about C? Okay, so for C, I would need a radius of convergence of at least 5. My radius of convergence in actuality has to be at least 4, but no more than 6. My radius of convergence could be 4 or 4.1 or something like that, and not be at least 5, making this part C not converge. But on the other hand, it could be a radius convergence of 6 or 5.5 or something, where this would converge. So for this one, we actually don't know. Not enough information. So we need a radius of convergence of 5. Our radius of convergence is somewhere between 4 and 6. It could be bigger than 5. It could be not bigger than 5. Not sure. We need more information to determine whether this one converges. What if I have an alternating series with a 9 to the n here? That actually doesn't do anything, right? Because I could just combine these two, and that's just a negative 9 to the n. That negative 9 to the n or positive 9 to the n, whatever, it's still symmetric about the center of 0. The negative 1 to the n doesn't really help or hurt anything. So it's really just this one that's doing all the heavy lifting. And again, we would need a radius of convergence at least 9 for it to converge here. But radius of convergence is at most 6. This must diverge as well. And this one can also be kind of tricky, part E. What about the sum Cn times 4 to the n? The radius of convergence is at least 4 because we converge for x equals negative 4. If the radius of convergence is strictly bigger than 4, even a tiny bit bigger than 4, then this must converge. But the radius of convergence could be exactly 4. If the radius of convergence was exactly 4, this would put negative 4 and positive 4 right at the endpoints. And we know that at the endpoints, we could be kind of plus or minus convergence, right? So knowing that we converge at negative 4 doesn't actually tell me whether we do or don't converge at positive 4. So I actually don't know. It's a bit similar to this one, right? Where we diverged at half a unit to the left, a radius of convergence to the left, but we converged half a unit or a radius of convergence to the right. So we could converge on a half open interval, or in an open interval, or in a closed interval. So knowing something about the convergence property at negative 4 doesn't help me out with positive 4, at least not in this case. Okay. It is possible that the radius of convergence is exactly 4 and that we don't converge at this endpoint. If the radius of convergence is strictly bigger than 4, even a touch bigger than 4, we would definitely converge. Or we could, if we had more information, we could evaluate whether this endpoint, if the radius of convergence was exactly 4, whether we should or shouldn't converge there, or whether we do or don't converge there. But in this case, not quite enough information to tell. All right, so let's move forward to 11.9 then. So representing functions as power series. So here I have an example, like a motivating example to start with. We have our good old geometric series. So if I consider the series sum n equals 0 to infinity x to the n, and I consider the domain restriction x in minus 1 to 1, I know that this series converges on this interval, open minus 1 to 1. It's a geometric series, and earlier we've actually worked out its formula. When it converges on this interval, we can write its sum as 1 over 1 minus x. Let me actually bump this down to the next line so that it shows up a little bigger for you. There we go. We can write its sum as 1 over 1 minus x. So we've thought of things going kind of this direction from right to left before, but this is an equal sign. We could also think of this going left to right. What if I was looking at the function 1 over 1 minus x, and I, for whatever reason, would like a power series representation for it. I would like to know, say, kind of roughly speaking, what CNs should I choose to make my power series match this function. And it turns out that this is the right way to do it, to make a geometric series if the function you're interested in is 1 over 1 minus x. We have something really, I don't know, I think it's kind of strange actually that kind of happens here though. 1 over 1 minus x equals, in some sense, this power series, this infinite series. This is a power series centered at 0. I know that 1 over 1 minus x blows up when x equals 1. I'm obviously trying to divide by 0 then. So, I mean, trying to say that a power series should be able to be evaluated at 1, that wouldn't make a lot of sense if I'm trying to represent a function that is not able to be evaluated at 1. But remember, my power series, this particular power series is centered at 0 and can't converge at 1. I mean, if it did converge at 1, it would be very silly to say that the power series that converges at 1 is a representation of the function that does not make sense at 1. So I have a power series centered at 0 that diverges at 1, but power series converge on symmetric intervals about their domain. The best I could hope for is what I get here. Well, I suppose essentially the best I could hope for is what I get here. That this equality, this representation of this function as a power series, as the geometric series, is really only valid on the open interval minus 1 to 1. This function, 1 over 1 minus x, has domain all real numbers except 1. I could plug 2 into it, I could plug negative 17 into it, no problem, for 1 over 1 minus x. This function over here, well, it has domain open minus 1 to 1. When we're doing this kind of thing, we're representing a function, kind of a standard algebraic function, as a power series. We have to be very, very cognizant of what the domains are. Quite often we're fairly lax in when we write down an algebraic function. I write f of x equals square root of x. We usually don't explicitly write the domain unless it's really important or noteworthy for some reason. We kind of, assume that, okay, we mean the natural domain for root x. So all real numbers bigger than or equal to 0, for instance. But here we have to be very careful and thoughtful about the domain because, well, I mean, for one thing, looking at the right-hand side, it doesn't, I mean, we know it's the geometric series, we kind of recognize this, but it doesn't jump out at you that, x equals 1 should cause a problem. I don't see any divided by 1 minus x's in the power series like I do over here, right? It's not so obvious at first glance that x equals 1 should be an issue over here. And likewise, if I look at this side of things, it doesn't seem like x equals 12 or negative 24 should be an issue. But this side, that doesn't work for. So when we represent functions as power series, we have to be very careful about what's the domain of the kind of algebraic function that we start with, what's the domain of the power series that we're representing it as, and that equality is only true on the intersection of those domains, where kind of both sides agree to take that input. So the domain on the left side is all real numbers except 1. The domain on the right side is only open negative 1 to 1, which also excludes 1. So the intersection of those domains, or the smaller domain in a sense, is just the open minus 1 to 1. So let's look at an example like this. Let's try to represent x squared over x plus 2 as a power series and maybe write out the first few terms. Okay, so x squared over x plus 2. I don't really recognize this straight off the bat as the sum of a power series that I'm familiar with. But I can do a little bit of algebraic manipulation here. I actually kind of noticed that, well, x squared over x plus 2 is x squared times 1 over x plus 2. We're starting to look a little bit like this left-hand side. I guess I could divide top and bottom by 2. So I could do x squared over 2 times 1 over, and let's flip this around, make it 1 plus x over 2. Close the parentheses. So I multiplied the numerator by 1/2 and just pulled that out and combined that with the x squared. I multiplied the denominator by 1/2 and distributed, and then I switched the two addends. And now it's looking even more like this. I have this annoying plus sign instead of a minus. It's not too often that I would prefer a minus to a plus, but in this case, that'll be helpful. And this is what I have. X squared over 2 times 1 over 1 minus negative x over 2. And what I see here, if I can even do a substitution or something, z equals negative x over 2 to make it very clear. I see this equals, I'm going to put in the information about the domain later, but you know, it might be a good idea to put it in now, but we'll remember to do that later. And this is sum n equals 0 to infinity of z to the n. Now, my left-hand side is only happy when x is not negative 2. My right-hand side is only happy when z is in open negative 1 to 1, or when x is in open negative 2 to 2. So this is the more restrictive domain. And of course, this is x squared over 2. Sum n equals 0 to infinity of negative x over 2 all to the n. That's what z is. This is for x in open negative 2 to 2. I could write it this way and leave it like this. I could also pop this x squared over 2 inside of the summation. Remember, we said that if a series converges, we can pop constants in and out. This is a constant in terms of n. This x squared over 2 doesn't have any n stuff in it, so it can pop inside. I get negative 1 to the n over 2 to the n plus 1 times x to the n plus 2. So I could write my series this way. If I really wanted to, I could even make this negative x to the power n plus 2, because multiplying by negative 1 squared to get a negative 1 to the n plus 2 and combine those two together just multiplies by 1. But I think we can leave it here. And I could write out the first few terms, say, you know, the second or third partial sum, something like that. So when n equals 0, I actually think it's probably easiest to start with this one up here and then do the distributive property. So when n equals 0, I have stuff to the 0 power is 1. when n is 1, I have this stuff to the first power. When n is 2, I have this to the second power, and so on. So that's the first few terms, or that's x squared over 2 minus x cubed over 4. The negative squares off, and I get plus x to the fourth over 8, and so on. Right, and it's a fairly common thing in a lot of the hard sciences to kind of take as many of these terms as you need, and then do like plus higher order terms. HRT is something you'll see quite often, and that's done with the intention of eventually getting rid of those higher order terms, maybe taking a limit or something, or maybe just making an argument that they're less influential to the overall problem, than is needed, that you can get plenty of accuracy with just however many terms you need. Okay, so we have an interesting theorem here. Suppose we have a power series centered at A, sum n equals 0 to infinity, Cn x minus a to the n. And suppose it has a radius of convergence r bigger than 0. Then consider the function represented by this power series. We can say the following about it. Note that what we assumed was we have a power series with a positive radius of convergence. That's our assumption. We can then say the following, that in essence, the power series is differentiable on the open interval of convergence, on a minus r to a plus r. Right? This function is a differentiable function. That's pretty cool. I mean, we didn't say anything about derivatives really at all up to this point in our discussion of power series, but we get differentiability out of this theorem. We can actually write out what the derivative is. And for power series, actually, we can differentiate term by term. We can essentially move the derivative inside the summation, right? What are we saying here? F prime of x is d by dx, sum n equals 0 to infinity, Cn x minus a to the n, right? It's the derivative of the sum. And what we're saying is that under this assumption, we're operating in the open interval of convergence, we can move the derivative inside of the summation. We know we can do this for finite sums, right? That's the derivative of the sum is the sum of the derivatives. Derivative is just a linear operator. But it's not clear if we can do that for infinite series, right? We saw that when we try to do even much more simple things like the associative property under infinite series, sometimes things can go very wrong. But what we're saying is we can pop this derivative inside. I guess I need another square brackets for the derivative. Yeah. We can move the derivative inside the summation if we're on the open interval convergence. And then, of course, this just brings the n down and puts an n minus 1 on top, right? Little side note that this series starts at 1 because really up here, our first term was a constant. So that differentiates off, and then our n equals 1 term is the one that sticks around. We also, of course, if we're a differentiable function, then we're continuous and therefore integrable. We also can integrate the function. And we can actually integrate term by term as well. Right? You see that this is just integrating term by term. And of course, we pick up a plus c when we do the integral. And also the radii of convergence for the two new series, the ones resulting from the derivative or integral, have the same radius of convergence. So pretty powerful theorem. You can move derivatives and integrals inside or outside of the summation when you're on the open interval of convergence. Okay, so let's try to find a power series representation for arctan. Now this is kind of annoying, right? Working with inverse trig functions is a huge hassle. I really don't want to try to set like y equals arctan x, so the tan y equals x, and then try to figure out a power series that way. I don't think that's going to be a good strategy. Can't really see a way forward there. What can I do here? Well, one thing I actually notice is in light of my previous theorem, I see that my toolbox has expanded. I have derivatives and integrals to work with now quite a bit more freely. The derivative of arctan 1 over 1 plus x squared is a heck of a lot easier to work with. What's f prime of x? What's 1 over 1 plus x squared, right? Or I note that that means that f of x is the integral 1 over 1 plus x squared dx. But okay, so 1 over 1 plus x squared, that's 1 over 1 minus a negative x squared. I didn't do any calculus here, just made that plus into a minus a negative. And this I see as 1 over 1 minus something. Well, this becomes the integral of the sum, n equals 0 to infinity. 1 over 1 minus something turns into something to the n power. Now, I do have an important note here. So 1 over 1 plus x squared, domain is all real numbers, right? 1 plus x squared is strictly positive, never going to be 0. Domain is all real numbers. But when I make this leap here to the power series, well, now I have a geometric series. Its ratio is negative x squared. That has to be in open negative 1 to 1. Now my domain is open negative 1 to 1. So this is crucial, right? We're not getting a power series representation for arctan like over the entire real line. We're uh, we have a domain restriction here because we're using the power series. Okay, but now I see that by my theorem up here, I can swap the integral and the summation. Be really aware here of kind of which letters are the variables in which contexts, right? The summation, its variable of interest is n, where the integral, its variable of interest is x. Okay. So this integral on the inside, its variable of interest is x. And now I can integrate negative x to the 2n, right? This is just negative 1 to the n, x to the 2n. So I can integrate negative 1 to the n, x to the 2n with respect to x. The negative 1 to the n, that doesn't have any x's in it. That just comes out of the integral. the x to the power 2n, how do I integrate that? This looks complicated, but it's just a power function. We add 1 to the power, we divide by the new power. And that is my summation. So what are the first few terms then? Again, kind of keeping in mind this only applies for x's in -1 to 1. So when n equals 0, I have -1 to the 0, so that's 1. X to the 1 over 2 times 0 plus 1 is over 1. When n is 1, I have -1 to the 1, so that's a negative. X to the 3 over 3. When n is 2, I have -1 squared is positive. X to the 5 over 5 minus x to the 7 over 7 plus, and so on. And we can see the pattern here, I think. So this is a power series representation for arctan x, but only good for x's between -1 and 1. One thing, one kind of minor note here that I want to throw in at the end is, what about c? What about our arbitrary constant? Well, f of 0 is tangent of 0, or arctan of 0 is 0. And if that's 0 plus c, we see that our arbitrary constant is 0. So I glossed over that point a little bit to just make the steps a little more clear as we're going along. Okay, let's look at this next example. Let's write x squared over a cubed minus x cubed as a power series. So what can we do here? We saw something similar to this already. I can break out x squared in front. I can divide top and bottom by a cubed. And I get that. And here I have 1 over 1 minus something. So we're really making use of the geometric series here, right? So 1 over 1 minus something turns into the sum of something to the n. And we could leave it like this, or we could bump that x squared over a cubed inside of the summation. That would be x to the 3n plus 2 over a to the 3n plus 3. And for what values of x is this valid? This is valid when the ratio x over a is in open -1 to 1, or when x is in -a to a. Or I suppose if I really wanted to be careful, I'd say minus absolute a to plus absolute a. I suppose a could be negative. So this would be our domain. As soon as we go from this step to this step, we've got to be careful to adjust our domain appropriately. Okay, let's take a look at this next example. writing 3 over x squared plus x minus 2 as a power series. So here I've got a quadratic in the denominator. One thing I might notice is that I can factor the quadratic, and I can actually apply partial fractions. So I'll spare you the details of partial fractions, but we end up with negative 1 over x plus 2 plus 1 over x minus 1. So this is just a little bit of factoring and partial fractions. We did nothing having to do with series or anything like that up to this point. This was just a regular old partial fractions problem. Like if this was under an integral sign, this would be the same series of steps we would do here. Okay, but now we see that, okay, I have two I have two components, this negative 1 over x plus 2 and this 1 over x minus 1, that have x's in the denominator that look like they can be matched up to our geometric series, wherever it is all the way up here. Look like it can be rewritten as something like a 1 over 1 minus x. The second one is actually really easy. It's just minus 1 over 1 minus x. Okay, that looks good. The first one is a negative 1 over, and then it will be 2 plus x, or 2 minus a negative x. And let's do a little bit more work here, just one more step. To get rid of this 2, we can divide top and bottom by 1/2. Oops, I left that a little too close to shimmy that 1/2 in there. So multiplying by 1/2 on the top brings a 1/2 out front. Multiplying by it on the bottom gives me a 1 minus negative x over 2. And then minus 1 over 1 minus x. Now I'll write each of these as a power series. So negative 1/2 times sum n equals 0 to infinity of negative x over 2 to the n minus sum x to the n. Now that I've kind of changed the form of my function in a really fundamental way, I need to reevaluate my domains. So this the second bit here is good for x in open minus 1 to 1. And the first bit, the first series, is good for x in open minus 2 to 2, when x over 2 is in minus 1 to 1. We'll pick the more restrictive of the two so that everything works. And that'll be our domain restriction. So when x is in open minus 1 to 1, we can make this change here, and that's valid. And now if we want to, we can maybe make this look a little bit nicer. So this can be what? Sum n equals 0 to infinity of, what would this be? Negative 1 to the n plus 1, x to the n over 2 to the n plus 1, minus sum n equals 0 to infinity, x to the n. And at this point, I have two series, both of which are convergent individually. And they're also nicely indexed the same. I can combine all of this under a single series. I guess I need a few more grouping operators there, but I can wrap it all under a single series if I wanted to. Okay, what do we have? 4 minutes. I think we can get the crux of this one. Okay. We might not do all the calculations, but we can get the idea. All right, so let's take a look at this integral. Integral 0 to 2/3, 1 over 1 plus x cubed dx. We know that kind of at best, this would be a very tricky and cumbersome integral to do, probably involving some kind of tray substitution and integration by parts and, probably several different steps that would be quite tricky. What if we only need an answer to 2 decimal places of accuracy? I suppose one way we could do it is the chapter 7 approximate integration methods. Could we use series to help us out here? Well, I might notice that 1 over 1 plus x cubed is 1 over 1 minus negative x cubed. And I could rewrite that using a geometric series. That's n equals 0 to infinity of negative x cubed to the n power. Or what is that? Sum of negative 1 to the n times x to the 3n. Is this valid on the whole real line or what? Well, no, I mean, we can see certainly that for x equals negative 1, our original function blows up. This is on only open negative 1 to 1. We need negative x cubed to be an open 1 to 1, so x has to be an open 1 to 1. Okay, so what about the integral then? So what about this integral? Well, let's start with looking at the indefinite integral on negative 1 to 1. So in the context that the evaluation or the domain restriction here is going to be that we're in open negative 1 to 1. So this is going to be integral of sum n equals 0 to infinity, negative 1 to the n, x to the 3n, dx. Remember that the summation is the thing that has n as the variable, and the integral is the thing that has x as the variable. And I can switch my order. That was what my theorem said, so long as I'm on the interval of the open interval of convergence, and I am. Then dx comes inside, and there we go. The negative 1 to the n just pops out in front. The integral is just a constant in terms of the integral. And then x to the 3n, remember the integrals variable is just x. This is just a power function. It's just x to some power. I add 1 to the power. I divide by the new power. I should also add maybe a plus c in here if I wanted to be careful, but I'm not really going to worry about that because I know that my goal is eventually to use this for a definite integral. So I just need an indefinite integral or an antiderivative. I don't need the most general one. So I'm satisfied with this, just picking c equals 0. And then, of course, I can see that integral 0 to 2/3, 1 over 1 plus x cubed dx, we're just about done here. I know that I'm 1 minute over, is if I give this a name, call it big F of x, this is big F at 2/3 minus big F at 0, that's 0. We just have to evaluate this at 2/3. It is an alternating series, nicely enough. So we can use our alternating series estimation theorem, figure out how many terms, how big of a partial sum we need, and just evaluate that many terms, and we've got our answer. Would it work if we're integrating over 0 to 2? No, because we would have to do big F at 2 and that is not in the interval -1 to 1. But because 0 to 2/3 stays within that interval, we're fine with doing this. Okay, so thank you for the couple extra minutes.